Swayam Prabha. Digital India. Educated India.
Today we will be talking about RG statistics. RG statistics specific to when we have RG centers as the mechanism for recombination and generation. Before this we have talked about recombination and generation in two cases. Basically we talked about all mechanisms which would lead to the generation of electron hole pairs, and we gave for change in the carrier concentration, especially if it is an optical generation. We gave the expression when you have optical generation, that is the dominant mechanism for generation. We also looked at when recombination from band to band transition is the dominant mechanism. We looked at the recombination rate or change in the carrier concentration in that case. But in addition to this, there is a very important recombination generation process which occurs in most devices, and that is recombination and generation, which is RG center mechanism. So, RG centers leading to the thermal RG mechanism. Since this is a very important mechanism for RG processes or recombination generation processes, we devote today's lecture to understand how would we mathematically look at the recombination generation using through the RG processes. So, effectively what we are saying is that we have looked at different individual processes individually, and we are still looking at individual processes. When you are working in a device, probably more than one will be working, and hence you will have to incorporate all the mathematical expressions that you need in order to understand how your device will work. So, today's lecture will be focusing on the RG statistics, or how RG centers lead to recombination or generation of carriers. So, basically what we are looking at is the mathematical characterization of recombination generation process that is via RG centers, which we have discussed in the earlier lectures. So, basically we are looking at, we would like to get a handle on how to deal with them in mathematical terms. Now, in the band diagram we had you know that for a semiconductor you have conduction band, valence band, edge, then either you have donors or acceptors, and then you mentioned that if you have centers in the middle, these act as traps or RG centers, and this is the effect of this centers. How does it affect change in the carrier concentration delta n over delta t or delta p over delta t is what we would like to do now. So, to simplify things first, let us assume not a large number of mid gap state, but maybe one single type of trap at a given level E t, and let us see how we can incorporate the behavior of this trap and the RG statistics that involves these two traps. So, with in this semiconductor, then we know few things. We know what is the equilibrium carrier concentration. So, we know N naught P naught, we know how to get that, N naught P naught, which is the equilibrium carrier concentration. we find also if carrier concentration through these RG processes is changing. So, N and P is the carrier concentration at any time at a given time, and then we also define axis carrier concentration del N del P, which is nothing but the carrier concentration at a given time minus the equilibrium, which is del N, or del P, which is P minus P naught. We further define, because we have put these RG centers which are the mid gap states, let us say N capital N T is the total number of RG centers in the semiconductor. In this total number of NT centers, we have small nt, which is the number of RG centers, which are number of RG center levels or RG centers filled with an electron. And small p t is number of RG centers which are empty. Or you can say they are occupied by the hole. So, you can see the relationship is that the total number of RG center will be equal to the number which is occupied by electrons plus the number which is not occupied by the electron. So, this would be the relationship in these parameters. Having defined this, let us look at how we are going to look at these processes. So, we are interested in finding out what would be the change because of the RG processes, what would be the change in delta N, delta T with time and in hole concentration with time. So, what are the processes that are happening because of these RG centers? So, let us look at it in detail. So, if this is conduction band, this is valence band and there is a RG center here, then one thing it can do is that it can capture an electron. So, an electron can be captured by this RG center. So, this is one process that it can do, which is capture electron. And other thing it can do is, once if it has a captured electron already, it can re-emit that electron. That is a second process, that is emission of electron. It can also do some other things, like it can capture a hole. So, if there is an electron here, it can capture a hole, and that is one process. This can also be shown as if the hole is getting annihilated by taking a hole from the valence band. Electron is coming down, taking a hole in a valence band, and this is basically capture of hole. The third process that it can contribute towards is capture of hole from the valence band. It can emit hole as well. So, one can think of a situation where electron from the valence band goes to the trap and leaves a hole. So, this would be the process by which electron goes to the RG center and thereby leaving a hole here. So, that is generation or emission of a hole. This is also sometimes seen as electron annihilating a hole. So, these are different ways of looking at the same thing. Basically, this is the same process by which you are emitting this is the emission of a hole in valence band. This is capture of hole from valence band. So, these are the basic 4 processes that a RG center can get involved in, and we are interested in looking at the overall effect of both recombination and generation together. What would be the net effect on the change in the carrier concentration? So, if I am trying to mathematically represent it, I can represent that as change in the because of this RG centers, this one particular one which we are considering right now. The change in the electron concentration is going to be change due to this capture process, which is going to be a del n del t change due to the capture process, first process, plus change emission because of the emission process, that is the second process. Similarly, I can write for holes this the mechanism of RG center. Overall effect of recombination generation would be change due to the third process plus the change due to the fourth process. So, what are these what are these rates for first 1, 2, 3 and 4 processes, and there we make certain approximations here and certain postulates on how we are going to model it. So, if you look at the process number 1, so if I want to now give some expressions for processes 1, 2, 3, 4, then if I look at the process number 1, what is that process doing? It is changing, increasing by capturing, it is decreasing the concentration of electrons in the conduction band, and how it will be decreasing that? It depends on how many electrons I have. It would depend on how many electrons I have in the conduction band, and what will it depend? It also needs empty trap states in order for the electron to combine with the trap states, which means the rate for the process 1 has to be proportional to the number of electrons in the conduction band multiplied by the number of empty trap states, which was given by P t as we defined that, and a proportionality constant for capturing of electrons C n, and this would reduce the electron concentration. So, with a negative sign. So, that is the rate for the first process. What would be for the second process? What does the second process require? It requires a state which already has an electron. So, you need, it has to be then proportional to the number of states which are occupied by electron, which we have defined as n of t, and that electron when it goes to the conduction band, it is basically a thermal process. It is decided only by the temperature of at that point. So, we will define that as the emission rate for electron, and by this process you are adding electron in the conduction band, and hence this is a positive. So, we have taken care of the first and the second mechanism, which changes the electron concentration in the conduction band due to the RJ process. Similarly, I can write the change in the hole concentration. The only difference here is being that my subscripts will change. So, here it will be the capture coefficient for holes multiplied by the P n of t, you need empty occupied states for that, and the emission of holes and P of t. So, these are the expressions, general expressions which take care of the net effect of all recombination generation processes due to the RG centers, which lead to a change in the carrier concentration. Now, this is a general expression which can be used in any device calculation or characterization facility. The only requirement here is this is for non-degenerate semiconductors. We are using this expression, deriving these expressions here for non-degenerate semiconductors. So, now let us look at if this is the case, if we have a semiconductor and we have a RG center in that semiconductor, what will happen in the case of the when we have a equilibrium. So, if we simplify this RG statistics for a equilibrium case, so equilibrium, what happens to those equations? Now, in equilibrium what is happening is that the number of electrons which are being captured is exactly being balanced by the number of holes which are being captured. The number of electrons which are being captured is being balanced by the number of electrons which are being emitted. Similarly, for the valence band, the number of holes which are being captured is being balanced by the number of holes which are being emitted to the valence band. Basically, equilibrium here means that each fundamental process is a detailed equilibrium. Each fundamental process is balanced by an inverse process. And so, basically what we are saying is that each fundamental process being balanced by inverse process means if the electron, this is a fundamental process as emission of the electron, then it is being balanced by capture of the electron, that is the inverse of that process. So, each of them will be balanced, which means this balance is going to be true for electrons and for holes separately. In other words, in equilibrium we are saying there is no change occurring due to RG center process. So, in equilibrium due to RG centers there is no change in the carrier concentration, this is 0, and the same thing can be written also for holes. So, let us look at the earlier equations that we developed in the case of the equilibrium, what will happen to it. So, if we equate the earlier equations to 0, we will get, for the case of electron, we will get C of n P T in equilibrium. I am defining it with a subscript 0. The concentration of electrons in equilibrium will be given by E, and this capture cross section, let me for the time being also define for the case of equilibrium as n 0. So, emission coefficient also with E n 0 times n T 0. Now, this equilibrium statistics basically is giving you a relationship between the emission rate and the capture rate. So, I can write the emission rate coefficient, and let me define them here, because basically what we had used in the last equation. C n is known as the capture coefficient, electron capture coefficient, and E of n is electron emission coefficient. So, now by invoking the equilibrium condition, we are able to find a relationship between the equilibrium coefficient in equilibrium and capture coefficient, emission coefficient and the capture coefficient in equilibrium. By the same thing, I can also write for the holes. This will give me EPO capture for holes in equilibrium, N of TO and PO over P of T. Now, although there is equilibrium capture coefficient and the emission coefficient for electrons and holes may change as things change, but we are going to make an assumption here, and we are going to assume that the E n remains similar to what its value is in the equilibrium, or C n also remains similar to its value in the equilibrium. Similarly, for E p for the holes, its value is close to what it is in equilibrium, and for capture of holes also its value is close to what it is in equilibrium. With this simplification, then I can write that E of n is equal to, that the emission coefficient, which I say remains similar to the equilibrium coefficient, will be C of n times n in equilibrium P T O over of n T O, and for holes the emission coefficient for R G statistics will be C of P n T O P O over P T O. Now, these values one can write this part and give it a name as E of n is this being called as n 1 for electrons, and for the holes the same thing is being called as this whole thing can be called as P 1. Then it becomes a shorthand, and we can write this as C n n 1. Now, n 1 is a new parameter. What this parameter is? N 1 is equal to n naught, which is equilibrium concentration of electrons, the number of equilibrium traps which are not occupied by electron divided by the number of equilibrium traps which are occupied by electron, and P 1 is P naught n of T O over P of T O. So, we have a more shorter notation for writing the emission coefficient in terms of the capture coefficient. So, now my with this expression that I get from the equilibrium statistics, I can write my equations for R G statistics in a more compact form, and this will be then del and del T due to R G centers. So, I have gotten the requirement. So, the general equation can be written now as negative of C of n P of T n minus n of T and n 1. And similarly, this is also for R G centers, will be written as C of P n of T P minus P of T P 1. Now, this expression let us discuss a little bit more about what this n 1 and P 1 is. N 1 and P 1 is something that we can calculate if we know how many traps, how many capital N T traps we have in the material. How we can do that? You can see very easily what is N naught. N naught is nothing but the equilibrium carrier concentration, and we know that this equilibrium carrier concentration is given by, so N naught and P naught are known. N naught will be given by Ni exponential E f minus E I, this we know from our carrier statistics in equilibrium, divided by K T. And what is N T O and P T O? That is the equilibrium N T O divided by capital N T is basically the number of traps which are number of trap levels or fraction of trap levels, this is fraction of trap levels with electron. Now, this we have earlier had an expression for when we are looking at the dopant. We had come up with an expression how many dopants are ionized at a given time. So, if we know the dopant level and we know the Fermi level, we can calculate how many dopants are going to be ionized. using the same equation we can also evaluate how many trap states are going to be ionized, and PTO is nothing but total of NT minus NTO. So, basically this expression N1 and P1 can be calculated, and now we have then RG statistics which can be written in this term, where we have basically starting from 4 rate constants. We have using the equilibrium condition, we have reduced it to 2 constant, which is the capture of electron and capture of the holes by the RG center, and this expression here. Now, equilibrium state is good to get certain simplification here, but in general most of the devices, when we are looking at the RG center mechanism, we are finding that most devices operate in the steady state condition. So, the steady state condition provides an interesting simplification of the RG mechanisms, and which is of interest to us, and that is why we would like to spend some time to figure out what happened to the RG center mechanism in the steady states. Now, in a steady state, like in equilibrium, each process had an inverse and it balanced each other. So, electron generation and recombination was balanced by the by its generation and recombination process were balanced. But in case of the steady state, the average values, basically what we are saying is that the average values in a steady state, average values of all macroscopic observables remains same. So, in such problems, basically what we are saying is, if the device has a electron concentration, then the electron concentration is not changing with time, or hole concentration is not changing with time. And in this case, we are talking about RG center processes. Basically then what it says means in steady state is that the concentration of RG centers which are occupied by electron, this is not a, this is 0. Basically the concentration of the trap centers which are occupied by electron is 0. So, if you have RG centers, which is a case that we are discussing here, the number which is occupied n of t and the one which is not occupied, which is p of t, this is not changing with time in a steady state. What does that mean? In a steady state, it means that the processes, the overall processes balance each other. Basically, in order to have this condition that there is no change in del n t, then what we are saying is that overall this means that this is equal to 0, which means that any change in the carrier concentration due to RG centers of electron plus any change in the carrier concentration of holes, if I add both processes together, there should be no change, which means n of t remains constant. So, that is a steady state condition. Now, if I apply the steady state condition to the RG statistics, then we are going to have equal number in words, basically we can say that there is equal creation and annihilation of electrons and holes. So, that is that condition. So, if we apply that condition, I can write my equation now. So, for del n by del t, I had an equation which says minus of C n. This is taking it from the previous page, where I got this particular expression. So, I would write that this plus this is equal to 0. So, minus C of n p of t n minus n of t and 1 minus C of p n of t p minus p of t p 1 is equal to 0. So, we simplify this expression and see what we can get. Basically, I am trying to get expression in terms of n of t. So, n of t is here, I can take that out. I will say n of t is basically C of n 1 plus C of p minus plus C of minus C of n p of t n plus C of p of t p 1. But we know that p of t is nothing but capital N t minus small t. So, if we substitute that here, what I am going to get is, and I will write the final expression here. So, I will get that the number of traps which are occupied, trap states which are occupied with the electrons is going to be equal to C of n small p t n plus C of p of t p 1 divided by the capture coefficient times n 1 plus whole capture coefficient times the whole concentration. Now, this expression is this is a total number of trap levels in a steady state which are occupied by electron. This is the expression for that. And from this particular expression, I wish to go to an expression which would change this in terms of, since I have both on both sides we have n of t and p of t, I would like to change that by utilizing this into only n of t expression. So, let me write the simplification for this. So, if I do that, I will write this whole equation as, after putting this condition in, I will get an expression which would give me n of t in terms of the total number of trap states, and that is given by C of n which is known to me, which is number of electrons in steady states times p 1 total number of trap states divided by C of n 1 plus n plus C of p plus p 1. So, I know what is my I know what is the concentration of trap levels which are filled. So, if I now want to calculate what is del n del t due to R G centers, the overall effect of annihilation and recombination generation in the case of R G centers, then del n of del t was nothing but minus of C n, p of t in the general case minus n of t and 1. Now, I have the expression for n of t. So, I would write this as minus of C n capital N t minus n of t and small n of t and 1. And in this now, I substitute the expression for n of t. So, I substitute this expression into this equation to find out what would be my del n del t. Now, the equations becomes, as you can see, the number of traps with electrons is a long equation. So, that the equations start running into 3-4 lines. So, instead of writing all the lines, let me give you the final answers, and which you can check that you will get the final answer. and in order to get the final answer I am going to make the substitution that N p is equal to N I square, which we know in equilibrium is always true. So, if we make that substitution, what I will find is that the del N del T due to R G centers, I can write an expression which is given in terms of N p minus N I square divided by N plus N 1 C of p, capture coefficient for holes, times total number of trap states plus p plus p 1, p 1 being whole p 1 being that constant we have discussed earlier, divided by C of n capital N t. Now, this is an expression which is going to be generally true. This is an expression that in a steady state it is going to define in a steady state the recombination rate for electrons due to R G center, recombination generation rate due to R G center will be given by this, and this gives us the opportunity to define another parameter, and that is basically this capture coefficient times N t. This we are going to define as 1 over tau of p. What is tau of p? Tau of p is nothing but it is the whole minority carrier lifetime. Similarly, we will define this quantity as 1 over tau of n, and that tau of n is electron minority carrier lifetime. So, in order to physically understand what these parameters mean, one has to think of what we have done. We have looked at a recombination generation net effect due to a R G center on electron concentration. So, let us see, let us take an example of maybe if we have, let us say a semiconducting material which has some N naught P naught, and it also has R G centers, and by some means I change the carrier concentration, excess carrier concentration delta N is equal to delta P, which means at some point t is equal to 0, let us say I increase the carrier concentration to N, which is N naught plus delta N, and change the whole concentration to P naught plus delta N plus delta P, and delta N and delta P are same for this particular mechanism that I am talking about. Now, since the I have put in some excess carrier concentration, depending on what kind of material it is, and let me, since in most times most cases in semiconductors we will either deal with one N or P type. So, if it is N type, then under the condition that I have low injection, either it is going to holes which are the minority carrier, there will be low injection level. So, minority carriers are going to be the delta P. So, if when I have increased the electron and hole concentration, it is a N type material, excess electron is not changing the C of the electrons which are there already in the material, but the excess holes that I have put in is changing the minority carrier concentration to P naught plus delta P, and that minority carrier concentration, if I leave after increasing this carrier concentration with time, would eventually relax back to Ni. It would like to go back to its equilibrium carrier concentration, and with the lifetime of tau p. So, that is what it means. It means when a carrier is in its minority role, what is the lifetime of the carrier, how long can it survive in the C of the majority carrier. So, tau n and tau p parameters, which are basically being defined by the mechanism of R G center thermal generation or recombination, are signifying if I create excess carriers in a material, how long the minority carrier can survive in the material before it is annihilated by the majority carriers. So, these terminologies which we have started with in trying to define the R G process, from here we get a physical meaning for what this term means, what this capture cross section then signify for the minority carriers. So, if you have a minority carrier minority carrier in a material, then this tau p is the average lifetime that minority carrier is going to survive. Now, then let us take this parameter as a material parameter. It is generally evaluated and experimentally obtained. One experimentally obtains this parameter, and so for a given material tau and tau p are calculated. Although you can see, if I know N t and I know the capture cross section for a particular type of impurities that we are talking about, this is something which can also be calculated, but generally one measures it, because Cp and Cn have to be measured. So, in terms of this then minority carrier lifetimes, my Rg statistics starts looking like change del N del T due to Rg process will be given by the mistake here should be N1 P1, otherwise this will become 0. So, N1 P1 minus Ni square. So, this will be given by N1 P1 minus Ni square divided by tau of P n plus N1 plus tau of N P plus P1. And similarly, you can say that in since we were discussing it in the steady state condition, this is for the steady state condition, this would also be same as for the Rg process for the holes. It will give the hole concentration as well. So, this is whenever you have device consideration for steady state, this is the expression one uses for finding out the carrier concentration change due to the Rg processes. Having discussed that, let us spend some time on what this parameter tau n and tau p are. These are basically electron or hole minority carrier lifetime. And they are being defined with respect to the presence of Rg centers in the material, and the important part of it is that most of the semiconductors, this Rg process will always exist, and hence this is an important parameter for materials. What is this dependent on? It is proportional to, as you can see, 1 over some constant times capital N of t. So, it is very interesting. It does not depend on how many electrons or holes are there. It depends on how many trap states are there. So, the minority carrier lifetime is not depending on the carrier concentration, but it depends on the trap concentration. And so, how many impurities or traps you have in a material will decide the minority carrier lifetime. So, typically if I take silicon, I would find the minority carrier lifetime can range basically tau n or tau p can range almost sub-seconds, microseconds in that range to the range of millisecond. So, depending on how many impurities, what is the purity level of the material is, this material parameter tau n and tau p can have a huge difference. And depending on what the application is, you would like your carriers either to live for a very long time, or you do not want them to get annihilated even before they get collected by either electrodes or have some subsequent action in terms of band to band transition or emission of light. Hence, these two parameters for a given material tau and tau p are very important, but they are important in the sense they are not intrinsic material property, they depend on n of t. So, they can be changed, they are dependent on the processing of the material. So, depending on how pure your material is, you will find the minority carrier lifetime can change within 4 orders of magnitude and that would change your that would define what kind of devices you have. So, if you have if you want a high speed electronic devices, you want very few number of traps in it, you want high carrier lifetimes. Even if you want a good LED, you want high carrier lifetimes, so that the light can come out by band to band transition rather than thermal RG center mechanisms for annihilation. So, this is tau n and tau p, and it comes out from the RG mechanisms statistics of recombination generation. So, to give a summary of what we have discussed and to connect it with some of the things that we have talked about earlier also. When we talked about the recombination process earlier for band to band transition, we were talking about band to band transition. There also we had a recombination rate which was proportional to 1 over tau. Now, this tau, which is the lifetime for the band to band transition, and we have discussed that what effect this tau will have in terms of recombination rates. So, if you have more than one processes, band to band processes, you are going to lose some light. So, if you have more than one process, then 1 over tau effective for band to band transition would be maybe a radiative transition, and if maybe there is some non-radiative transition. So, this was the lifetime for band to band transition. This was for electron joining with the hole, it is a recombination process giving you a photon or heat, and that was the lifetime, that tau effective that we had looked at. But as we discussed even at that time, in the semiconductor there are probably more mechanisms, and if it is a direct band gap semiconductor, you would have band to band, plus you would always have this RG center mechanism. And in this RG center mechanism, we just looked at what these RG centers do. So, the thermal RG center mechanisms can affect at a given point what would be your minority carrier lifetime going to be. It is inversely proportional to that. So, the tau n or tau p is inversely proportional to 1 over n t, and there is a lifetime associated with it, which is different. This is the minority carrier lifetime. Minority carrier lifetime is related to the RG center mechanism, and this should not be confused with the radiative lifetime which we discussed earlier. Basically, what we have been doing is we have been looking at single processes and giving you how to deal with it mathematically. But if you would have a material where more than one processes are available, then you will look at the band to band transition, which may be giving you the light out, and also add the RG center mechanism to that, which you will see. Then if you have more than one mechanism, you would write the equation for del and del t for different mechanisms. So, basically in this lecture we saw that if we have RG center mechanisms, then in a steady state we have an expression that would be very useful. We have a general expression also, and then we derive for a steady state. You can write this as this expression in terms of minority carrier lifetime, which is given by tau of p and plus and 1 p plus p1. So, this is a general expression in a steady state that can be used while calculating device characteristics. Let me now take an example to show you that this general condition that we have derived for steady state RG mechanism, if we look at in a special condition, it will give you exactly the same solution that we derived for looking at band to band transition or some other mechanism. So, the special condition that we want to look at for the steady state solution, special case we will look at for low level of injection. So, this we show an example to show that this this whole equation can gives you the finally the same answer for the special case. So, we have the recombination rate in a steady state, which is being given as n 1 minus n I square divided by tau of p n plus n 1 plus tau of n p plus p 1. So, generally as we said, we have a normally one majority carrier. So, let us say if this is a n type semiconductor, basically that is saying that my n is much greater than p, and with this condition I also see that n 1 and p 1, which we know the expression for it. So, n 1 is we say is roughly close to p 1 is also very close to n I. N 1 is similar to p 1 is approximately close to n I. Then I can expand this for a n type semiconductor. The n 1 p 1 is going to be equal to n naught plus delta n times p naught plus delta p, and I am creating a situation where injection level is low. So, del n or del p is much less than n for a n type semiconductor. So, for low level of injection. So, if this is true, then this would be n naught plus delta n, p naught plus delta p minus n I square divided by tau of p. N can be written as again n naught plus delta n plus n 1 and p as p naught plus delta p plus p 1. Now, applying the condition for low level injection and the other conditions for which we know that n naught p naught is equal to n I square. If I expand this, I will get n naught p naught plus n naught delta of p plus p naught delta of n plus delta n delta p minus n I square. You can immediately see that this cancels, and in the denominator I still have n naught plus delta n Now, since this is a low level of injection, one can immediately see that only this is going to be very negligible. This is going to be very negligible, and since it is a majority carrier device, p naught is much smaller. So, this is going to be very negligible. The only thing that is left is n naught delta p from the numerator, because other quantities are going to be very small. The same way, if you see the denominator, since it is a majority carrier device, this is going to be always much larger than this value, and within this also this is going to be always much larger than these values for a n type device. Hence, you would get n naught tau of p, and you can see this nicely, this expression for steady state recombination rate reduces to what we have earlier derived for band to band transition to a exponential decay of excess carrier concentration with the lifetime. And so, you can see why you have similar expression obtained in the special case of low level of injection. It is also important here to mention that if we did the dimensional actions all the time, or if we looked at the dimensionalities also all the time also, the tau of p, which is defined as 1 over capture cross section for C p times n of t, the dimensionality is such that this is in terms of seconds and this is in terms of per centimeter cube, which means the units for the capture coefficient is basically 1 per centimeter cube per second. And you can check this, that even in earlier equation, that this particular dimensional units for Cp will would be correct with the earlier processes that we have discussed from the beginning. So, tau actually comes up getting a unit of a second, and that is kind of a lifetime for the carriers that we get. And in the low level of injection, our general expression for a steady state does reduce down to what we have derived earlier for special cases of low level injection when we have certain rates. So, this gives us a good consistency with whatever we are deriving has similar expressions coming out, or they come down to matching with what we get in the special cases.